Okay, so here let's see how we can use the potential method to also derive this equation. But actually I used to this method rather than the energy method. But yeah, I think the energy method is quite interesting. So just let you know both ways to get the same result. Okay, so here for the circuit we have L and C are in series. So this circuit only have two nodes, 1 and 2. So we can define either of them to be a ground node. So which means that the potential of this node is 0. Okay. So in that case, this is a single loop. So we only have one current. So let's assume this current is clockwise, and this voltage is V, which means that this is V if you consider this node subtract this node, I mean the potential. The potential of this node subtract by the potential at this node will be V. Or likewise, if we have V and then plus minus, and then it should be negative V. Then it should be negative V. Why we need to do this is the current direction is in this direction. So if we'd like to make everything correct, then this is plus, this is minus, and then we have a negative sign. So this V and this V are the same, but we have a negative sign here. Yeah, of course, when I'm very familiar with it, I don't really need it necessary to explicit why this is V, this is negative V, and yeah, I still get the same equation. But if you are not so familiar, let me try to write it in very detail so that you don't really make mistake here. Okay, so here, when you see the current is clockwise, so this is I. So according to this capacitor, we can write it as I equals C dV dt. Okay, for the capacitor. And then for the inductor, we have a V equals L di dt, but here this one is negative V. Or maybe you can say, this is VL equals negative V. V is a variable. Okay, so actually this one is like negative V equals L di dt. Yeah, because we need to follow direction. So the current here is like I is pointing upward. So this is plus, this is minus. So this is V. This is negative V when you consider this inductor, and then with this current direction. Okay, so here we have two joints, first order ODE, and then of course we can just substitute one into another, and then we can finally get an equation. Okay, although this equation is like is in terms of Q, we can just we can just do it here like we try to, let me see, we try to substitute this equation into here. So because we have, this is I, this is I, so we just substitute the left equation into the right one, and then we can eliminate I. So in that case, here we have a C dV, it should be like negative V, because we try to substitute this one into here. So on the left side we have a negative V equals L di dt. So here is di dt, so we try to substitute this thing here. So we have a C dV dt. That is. Okay, so as much as C is independent to T, so we can just put C out, which means that we have a LC and then ddt dV dt. So it will become the second derivative of V with respect to time. So in this case, we can just move this term over and then dV divide both sides by divide both sides by LC. So in that case, we have a d2v dt2 plus 1 over LC v equals 0. Okay, so I'll compare with the previous equation. This equation is related to V, and this equation is related to Q. But as much as I've mentioned, this is so-called constant coefficient linear ODE. Because this circuit is linear, it only consists of sources, like voltage source or RLC are so-called a linear element. So in that case, it is a linear system or linear ODE. And in that case, if you try to write an ODE governing the linear system, okay, so in that case, you can write like d2v dt2 plus 1 over LC, v equals 0. Or simply, you can also get d2i dt2 plus 1 over LC, I equals 0. Okay, so for any variable in the circuit, you might be able to write the same form of ODE, same form of ODE. So you can see a second derivative of V plus 1 over LC is the coefficient, and then V, so this V and this V. And then here, also the second derivative of I, and then plus 1 over LC times I equals 0. So just change the unknown function. So here also Q is the unknown function. And you can also see the analogy. So here we mentioned this is LC oscillator, this is a spring mass system. Okay, so you can also derive the equation like this. So as much as like, so you have a spring connected with a mass. So this is K, the mass is M, and then the coefficient of the spring is K. So according to the Hooke's law, we have F equals negative Kx. So according to the Hooke's law. And then according to Newton's second law of motion, you know F equals ma. So F equals ma, m times a is the second derivative of the displacement with respect to time. So we have F equals m d2x dt2. Okay, so here you can see this is an second order ODE. And if we just divide both sides by m, and then move this term over, we will get d2x dt2 plus k over m times x equals 0. Okay, so this is also a second order ODE. And of course, if we would like to solve the second order ODE, what we look to find is the characteristic equation, which means that we try to change the second derivative will be s squared and then plus k over m, and then change this original function to be 1. So just like this. So s squared plus k over m equals 0. Okay, so in that case, we have s to be plus or minus j, and then times square root of k over m. Okay, or maybe we can just define omega 0 to be square root of k over m, so that this is nothing but plus or minus j omega 0. Okay, so if you forgot, j is negative square root of negative 1, or usually you might know it as I. Okay, so as much as this is a complex conjugate root, which means that x should be something like a cosine omega 0 t plus b times sine of omega 0 t, something like this, because this is a complex conjugate root. And yeah, actually you can if you are not so familiar, I would say that it is something like 0 plus or minus j omega 0. Okay, so which means that the real part is 0. So in that case, you know this is alpha, this is beta. So the general form of this one is like an exponential to alpha t, and then a cosine of beta t plus b sine of beta t. Okay, so as much as alpha is 0, so this is 1 when alpha equals 0. Okay, so in that case, we only have these two terms. And of course, you can just write it as r times cosine of omega t plus phi. So according to some high school trigonometry identity. But simply speaking, if you just choose a proper time, so you can just ignore this phi. So simply speaking, you can just write it as r times cosine of omega 0 t, or sine. It depends on how you choose the reference time. So in the textbook, you just write it as this. So it also tells you that it is something like this. Okay, so we have r cosine omega t plus phi. So here it also tells you that the solution to d2 q dt2 plus 1 over LC q equals 0. Okay, the solution is like this. So capital Q multiplied by cosine omega t plus phi. Okay, just as what we have here. The only difference is that for the spring mass system, omega 0 is a square root of k over m. Here, this omega is 1 over square root of LC. So if you just try to solve the equation here, we have s squared plus 1 over LC equals 0. So we have s equals to plus or minus j, and then times square root of 1 over LC, which means that here omega is 1 over square root of LC. So this is the difference between the LC oscillator and the spring mass system. So the oscillating frequency depends on the L value and also the C value. And for the spring mass system, it relates to the spring coefficient and also the mass of the object. Okay, so this is Q, and also you can just use I equals dq dt, and then you plug in this one into here, take the derivative. So you have a dq dt is d dt and then q cosine of omega t plus phi. Okay, so this is a constant, so we have q here, and then cosine, take the derivative, will become negative sine omega t plus phi. And then don't forget the chain rule. The chain rule take the derivative for the argument of cosine. So with respect to time, so this is a constant, so it vanishes. And then take the derivative of this one with respect to time, you have another omega here in the front. So finally you get a negative q omega q times sine of omega t plus phi, something like this. Okay, so if you just plug in q into this identity and also this identity, so UE equals q squared over 2c, and then you plug in the expression of q here. So you get q squared cosine squared omega t plus phi, and then here you have a q squared over 2c, q squared over 2c, or it is like this one is like 1/2 Li squared. So here you get I has this expression. So I squared will become omega squared q squared, which is like 1/2 L and then omega square q square, and then here also we have a negative sign, so the negative sign square will become positive, so we only have a sine square cosine omega t plus phi. Okay, so the remaining stuff is here. We already have a q square, so the only remaining thing is that we also have, this is 1/2, this is 2. Okay, so the remaining terms are L omega square. And if you still remember, omega square is, omega is a 1 over square root of LC. So take the square, okay, and then we will have L and L cancel. So the only remaining terms is 1 over C, so which matches this C here. Okay, so the interesting thing is that, so UE is like, this is cosine square, this is sine square, so just ignore it first. So we have q square over 2c, q square over 2c for both UE and UB. So which means that if we just add them together, you know sine square plus cosine square is 1. Okay, when you learn the trigonometry in high school, this might be the very first identity you have learned. So which means that if you just add UE and UB together, so the sum, so combining these two, you have a UE plus UB to be q square over 2c. So this means it is a constant. So this q is like the amplitude of the oscillation, the amplitude of the charge of the oscillation. So this is a constant, and then c is also a constant. So this whole thing is a constant, which means that the energy doesn't change, which matches what we assume at the very beginning, because at the very beginning we assume that U equals UB plus UE is a constant. We have a dUt dt equals 0, so the U shouldn't change. And finally, after solving the expression of Q, and then you finally plug in back to here, you really find that, oh, this is true, UE plus UB is constant, and the constant is capital Q square over 2c. Okay, so it says the maximum value of UE and UB are both Q square over 2c. At any instant of the sum UE and UB is equal to Q square over 2c, a constant. Okay, constant. So when UE is maximum, UB is 0, and conversely, because this is a square, which means that it should be between 0 and Q square over 2c. Yeah. Okay, so here we have a sample problem. So it says a 1.5 microfarad capacitor is changed to 57 volt. The charged battery is then disconnect, and a 12 millihenry coil is connect in series with the capacitor, so that as the oscillator occurs. Okay, so here we have a capacitor value and the inductor value, and it's charged. So this is the initial voltage. Okay, so it asks what is the potential difference VL across the inductor as a function of time. Okay, so at the very beginning we have a d2q dt2 plus 1 over LCQ equals 0. So this is the trivial expression, and then we have the solution to be Q equals capital Q, and then times cosine omega t plus phi. Okay, or maybe we just ignore the phi here. We just assume that phi to be 0 for simplicity. Okay, you may ask why we can assume this, but here we don't really concern about the timing, so we can just pick a t, because we just consider the amplitude. Yeah, we don't really concern about the time. So if we just pick phi to be 0, it makes things easier. Yeah. Of course you can still keep the phi there too. Yeah, but it is not necessary for this question. Okay, so in that case, Q equals C times V. C times V. V is actually this one. So we have 1.5 times 10 to negative 6, and then times 57 volts. So we have 8.55 times 10 to minus 5 coulomb. Okay, so this is the charge, the amplitude of the charge. And in that case, we can just calculate VL by L di dt and L di dt. Here we don't know I yet, so actually we have I equals dq dt. I equals dq dt, which means that okay, we can just plug in this one to here. So we altogether have L, the second derivative of Q, and then with respect to time, like this. Okay, so here, if we just click the second derivative of Q, so d2Q dt2, okay, so it becomes, okay, 2 times the chain rule, we have omega squared, and then Q. And then second derivative of cosine squared, so it becomes negative sine and then negative cosine. So finally we get a negative omega squared Q and then cosine of omega t. Okay, so in that case we have negative L and then Q omega squared and then cosine of omega t. And then we can just plug in omega to be 1 over square root of LC, which means that omega squared is 1 over LC. So we have a negative LQ and then 1 over LC and then cosine omega t. So we can do some cancellation. We cancel this L with this L. Then we can finally have it to be negative Q over C and then cosine of omega t. Or actually this Q over C is nothing but V. It's nothing but V. So finally we have a negative V cosine of omega t, which means that it is something like which is negative 57 and then cosine and then t over square root of LC. Omega is square root of LC. Omega is 1 over square root of LC. So we have 12 times 10 to minus third. This is L and then times 1.5 times 10 to minus 6. This is C. Okay, so this is LC, which 1 over square root of LC, which is omega. So finally, we get a negative 57 cosine 7,500 T. And then the SI unit is V. Okay, so this is the final answer to question A. Okay, VL of T. Of course, this is a radian. This 7,500 is in radian per second. Radian per second. It is not a linear frequency. It is a radian per second, which means that omega. This is omega. It's like 2 pi f. 2 pi f. So if you would like to see what is the frequency, you need to divide this 7,500 by 2 pi, then you get the frequency, which means that how many oscillation is in 1 second. Okay, so for part B, what is the maximum rate didt max at which the current I change in the circuit? Okay, so we have I equals dq dt. and then it turns out to be negative omega q sine of omega t. Okay, of course we have already explained this equation here, so I do not repeat it again. Just plug in q to be capital Q times cosine of omega t. Okay, you get this one. Okay, so and then when you try to find di dt will be like negative omega q, and then sine, the derivative of sine is cosine omega t, and then the chain rule, you take the derivative of the argument, so you get another omega. Turns out to be like this. Okay, so ask what is the maximum rate at which the current I changes in the circuit, which means that if just say cosine of omega t to be plus or negative 1, and then this is the maximum rate. This is the maximum rate, which means that di dt max is like omega squared q. Just let this one to be plus 1 or negative 1, because we have a negative sign in the front, so which is like cosine omega t to be negative 1. Then yeah, this is the amplitude. And then you can see omega squared is 1 over LC and then times q. So we have q over c to be v, because q equals cv or v equals q over c. So this q over c is v. So we will get v over L, which is 57 over L is this one, 12 times 10 to the negative third power, which is 408,000 ampere per second. Okay, why the SI unit is like this? So you see here di dt. So the SI unit for I is A, the ampere. The SI unit for T is S. So the SI unit for di dt max is A over S. Okay. Any questions? Okay, if no, we go to another more complicated situation, which is called a damped oscillation in an RLC circuit. Okay, so in Chinese it is called 阻尼 oscillation, damped oscillation in an RLC circuit. Just now we have LC oscillator. Here we have RLC, which means that we have resistance. So in that case, there will be some energy loss. And then you can see here, we still have L and C in series, but in between we have R. We don't necessarily connect a resistor there. We just consider the intrinsic resistance inside the circuit, because except superconductor, there must be some resistance, even for the inductor or capacitor, or even the wire, it should have some resistance. So we just try to consider all the resistance in the loop to be a single resistor, and then we model it here. So we put it here. We don't actually put a resistance there. We just consider the total intrinsic resistance within the circuit, and it will have some resistance. So we have a resistance here, and then you can see some curve with red color, which means that this resistor will consume energy stored in the oscillator, and then it turns out to be some heat, okay, and then dissipated. So it says to analyze the oscillation of this circuit, we write an equation for the total electromagnetic energy U in the circuit at any instance. Because the resistance does not store any, EM energy, we can write it like this. So for the first step is actually the same as the previous case, but here we don't have du dt equals 0. Rather than that, however, the total energy decreases. The total energy decreases as energy is transferred to the thermal energy. The rate of the transfer is this one. Okay, because the power consumption of the resistor is P equals I square R, which means that in that case, du dt will be negative I square R, because it's consumed the power, which means that the energy change, the rate of change of the total energy inside the circuit will be a negative value, because the energy is consumed by it. So we have negative I square R, like this. So in that case, du dt, so as much as in the previous case, du dt will be something like LC d2q dt2 plus q. Is it that case? Okay, for du dt. It should be something like this. It should be something L di di dt, qc dq dt. Okay, let me just copy it out. Okay. Yeah. Okay. It is like Li di dt plus q over c dq dt. Yeah, this is what we had previously. And then we also have du dt equals negative I square R. So which means that the right side of both equations equal each other. So which means that we have Li di dt plus q over c, and then dq dt is actually I equals negative I square R. So we can just cancel all the I. Yeah, I and I can be cancelled. Okay, so for the so we just move this term to the left side, and then we can see this is di dt, and also we have I equals dq dt. Okay, which means that for the first one, L di dt is nothing but L d2q dt2. Okay, this is the first term, and then for this one, okay, I is nothing but dq dt. So we have R dq dt. Okay, for the second term. Okay, and then for the final term, this one, q over c is nothing but itself. Q over c equals 0. Okay, so we just divide L on both sides. So we have a dq dt, d2q dt2, and then R over L dq dt. That's the second one, and then Q over LC. Q over LC equals 0. Okay, so we get this one. Okay, so if we don't consider this resistor, we don't get this term. But here, when we consider the intrinsic resistance, if we consider intrinsic resistance, so which means that this term is related to the resistance. resistance. Okay, so it makes things more complicated. It makes things more complicated. Okay, so in the textbook, it just tells you that, okay, the equation, the solution to this second order ODE is like this. Okay, and then omega prime is something like this. Omega is still this 1 over square root of LC, which means that here we call this omega prime the natural frequency, or the natural angular frequency. This one is slightly less than omega. Okay, omega prime is less than omega. If we don't have this resistor, this expression is very, very easy, which is nothing but 1 over square root of LC. But here we have omega squared. If you consider this term to be a very small value, which means that omega squared minus something and then take the square root. So in that case, it will be slightly less than omega. And of course, this one is related to resistance. We don't expect this resistance to be very large. And we also hope this L to be large, so that this term won't be very large compared with omega. And then we'll see how we can really derive it. Okay, so for the potential method, okay, we can try to write out the ODE. Okay, so here we have this is VC, and then this is VR, and also this is VL. Okay, so we consider this is the direction for the KVL, and then we can just pick this point to be the ground, and then the current is in this direction. So according to KVL, we can write that VL plus VR plus VC to be 0, because this is plus minus plus minus plus minus. So we just add through VL, VR, and VC, and then to complete a loop. So the VL plus VR plus VC to be 0. And we can also write that for the inductor. For the inductor, we have VL to be L di dt. And then for the capacitor, we have I to be C dV C dt. Okay, so we altogether have this 1, 2, and 3. And you can simply expect that we can try to eliminate some of the variable, because we have many variables. We have VL, VR, VC, and also I. We are altogether have 4 variables. So here we have 3 equations. So we also need to have VR to be I times R, I times R, okay, which is nothing but the Ohm's law. So I always say that the resistance are the easiest element. So it is nothing but V equals IR. But for the inductor and capacitor, it has so-called memory with memory. Has memory, which means that this voltage depends on the current now and the current in the past. So, which is the derivative, and also the current for the capacitor related to the voltage at the present and also in the past. So the derivative of the voltage. Okay, so in that case, we can try to do some substitution. Okay, let's see how we can do it. So let's plug in this one there. So VL, the first one is VL. VL is L di dt. So we have L di dt, and then plus VR. VR is nothing but I times R, or R times I. Okay, and then plus VC. Okay, so we just let it VC because we cannot put this one there. Okay, so here let's try to derivative. Take the derivative, then it will become L, the second derivative of I, dt2, and then plus R, di dt, and then plus dvc dt. Because we just try to form this one out, and then we can just plug in this one to be I. We still want another C, so we just multiply C on both sides. We have a C, C, and C. So that we can just form, okay, just form C dvc dt on the left side, which means that this is nothing but I. This is nothing but I. Okay, so in that case, we have LC d2I dt2 plus RC di dt, and then plus I to be 0. And then we can divide LC on both sides. So it turns out to be d2I dt2 plus RC over LC. So it becomes R over L, and then di dt plus 1 over LC I equals 0. Okay, so it just take the similar steps. So we try to change second derivative to be S squared plus R over L. And then this is the first derivative, we change it to S, and then plus 1 over LC. The original one, change it to 1. So it's nothing. Okay, so this is the characteristic equation for this second order ODE. Okay, and in that case, we try to solve it. We will just discard delta to be larger than 0 or delta to be 0. Okay, we just don't consider these two cases, because for these two cases it's not so useful for us, because when delta is 0, the solution will be like exponential to minus exponential to s1t a times, then plus b exponential to s2t, just exponential decay. We will expect this circuit will oscillate, so it should have something like the sine wave, and either for this one it will be something like a plus bt exponential to s1t, so it's still exponentially decay. So we don't like these two cases. So the only case we consider is delta is less than 0. That's why when I try to tell you why there are 3 cases, but actually this one is the most complicated one, and also it is most useful because it has something like the complex solution will be correspond to a sine wave. Okay, so in that case, when we try to solve it and we assume it to be complex solution, so S will be like okay, so here we have 2, A is 1, so we have 2 in the denominator, and then we have a negative B is negative R over L, and then plus or minus. Yeah, we already assumed that b squared over 4, b squared minus 4ac is negative. So here we should have 4ac minus b squared, and then square root, and then times j. J is square root of negative 1. So we have 4ac. 4ac is, a is 1, c is 1 over lc. So we have 4 over lc. 4 over lc minus b squared. This is b squared. So we have a r squared over l squared. Okay, so we just distribute these 2 here and also 2 inside the square root. So we will have negative r over 2l, and then plus or minus, we still have a j, I forgot. Okay, so maybe I just put j in the front, and then square root of Okay, 2 putting inside the square root become 2 square. So cancel with the 4. We have 1 over LZ and then minus R over 2L and then quantity square. So this is why we have something like this. So you can see this is the real part. This is the real part. This is the real part. This is the imaginary part. This is the imaginary part, which means that I should have the expression like I and then exponential to the real part times the t. So negative RT over 2L. And then originally it should be something like A cosine plus B sine. And similarly, you can just change it to a complete cosine. So it becomes cosine omega prime. So we define this one to be omega prime. It becomes omega prime t plus phi, something like this. We don't need this parenthesis. Okay, so this is omega prime, and then this is actually 1 over omega. This term is actually omega square. This is omega square. Omega square is 1 over LC. That's why omega square is square root of omega square minus R over 2L square, which is this one. And then the expression is like this. Originally, it should be like exponential to alpha t and then A cosine omega prime t plus B sine omega prime t. Should be something like this. But yeah, according to the trigonometry identity, this one can be written as I and then exponential to alpha t and then cosine omega prime t plus phi, something like this. That's why we just write it here. Okay, so yeah, okay, I think I have finished this part. Okay, so let's have a 10 minutes break and then we move on.